All right, today we're going to tear down a really cool standard, one that's trying to create a universal language for the trillions of sensors all around us. We're talking about IEEE 1451.
So, to get our heads around this, let's take a quick trip down memory lane. Do you remember that junk drawer everyone used to have, just tangled with old phone chargers? You had one for your old Nokia, a completely different one for your Motorola. None of them worked with each other. It was just a complete mess, right?
Okay, now take that same exact frustration, but scale it up, way up. Imagine that problem for every single sensor and actuator. You know, the little devices that measure stuff and make things move, that are basically running our entire modern world. That's the kind of compatibility chaos we're talking about here.
And look, we're not just talking about a handful of gadgets. Sensors are literally the nervous system of our planet now. They're inside our factories, our cars, our homes, our hospitals. I mean, they are absolutely everywhere. And for decades, pretty much every single one of them spoke its own unique proprietary language. But what if there was a universal translator? You know, like a USB for sensors that could make any sensor talk to any network. Well, guess what? That is exactly what the IEEE 1451 standard is designed to be.
So what is this thing, really? Well, at its heart, IEEE 1451 is just a set of rules, a kind of blueprint that lets smart sensors communicate in a totally standardized way. It's all about creating one common interface so that parts from totally different companies can understand each other, you know, right out of the box.
And this slide, this really shows you the before and after. Before the standard, you were pretty much locked into one vendor's ecosystem. If you wanted to add a new sensor, it was this huge, complex, custom integration job. The whole point of IEEE 1451 is to flip that script completely. We're talking true plug-and-play capability, where you can just swap sensors in and out, simplify your designs, and build these wide-open, interoperable systems.
So how does it actually pull off this magic trick? Well, it's pretty brilliant, actually. The standard breaks down any smart sensor system into three logical key components.
This diagram really lays out the core idea beautifully. You've got the sensor part, the processor in the middle, and the interface that links them together. We're going to break down each of these three little acronyms you see here: STIM, NCAP, and TII.
Okay, let's start with the STIM. The easiest way to think about it is like a smart adapter for your sensor. It's the piece of hardware that lives right next to the physical sensor itself. It does the first bit of processing, and most importantly, it holds the sensor's digital passport.
So what's actually going on inside this STTM? Well, it takes that raw analog signal from the sensor, or transducer, which is just a technical term for something that converts energy, like pressure, into an electrical signal, and it turns it digital. But its real superpower is something called the TEDS, the Transducer Electronic Data Sheet. This is like the sensor's complete resume, storing everything from who made it to its exact calibration data. It's all right there.
And this is just perfect for showing how it goes from idea to reality. On the left, you've got the engineer's blueprint, the schematic for a STIM that monitors different gases. And on the right, that's the real deal, the actual circuit board that makes the magic happen. So cool to see it go from theory to a physical thing.
Okay, next up, the NCAP. If the STIM is the sensor's personal adapter, then the NCAP is the system's brain, or maybe a smart hub. Its whole job is to talk to all the STIMs, gather up their data, and then pass that information along to a bigger network, like the main computer in your factory or up into the cloud.
And this is where the system really gets powerful. A single NCAP can act as a gateway, collecting data from a whole bunch of different STIMs. Maybe one's measuring temperature, another's checking pressure, a third is looking at humidity, and the NCAP just gathers it all up and funnels it to the network.
The last piece of this puzzle is the TII, the Transducer Independent Interface. This is basically the communication link, the cable that connects the STIM to the NCAP. And the most important word here, you guessed it, is independent.
If we look back at our main diagram, the TII is this bridge right here. And because it's independent, it doesn't care how the STIM and NCAP are connected. It could be a physical USB cable, a wireless signal like Zigbee, or a standard Ethernet connection. The standard separates the sensor from the network, and that simple idea is the key to all of its flexibility.
Okay, so that's the how it works. Now let's get to the fun part, the so what. Where is this standard actually being used to make a difference out in the real world?
Well, the applications are just incredibly diverse. We're seeing the standard pop up in everything from factory automation and smart buildings to really complex aerospace testing and even medical devices. Basically, anywhere you need reliable, interchangeable sensors, this standard has a major role to play.
This table gives you such a cool snapshot of that variety. Just look at this. For gas measurement, one project used an old-school parallel port. For a system inside a car, they used CAN bus. That's the standard for automotive electronics. For industrial automation, they used wireless stuff like Zigbee. The sensors are different, the communication methods are totally different, but IEEE 1451 is the common framework that ties it all together.
And here is a great, really concrete example. This is the diagram for a wireless air quality monitor. You can see the sensor array, the processing unit, and a Zigbee module to beam the data out wirelessly. It's a perfect, real-world implementation of everything we've just been talking about.
And don't think this is just for slow, simple data streams. This standard is seriously robust. If you use a common connection like USB 2.0 for that TLI interface, you can hit data speeds up to 480 megabits per second. That is plenty of bandwidth for even high-speed, really demanding applications.
So with such a powerful standard already in place, what does the future of all this connected sensing even look like?
Well, the vision for the future is even more integrated, if you can believe it. Researchers are already imagining STIMs with GPS built right in for location-aware sensing, or even STIMs with their own little screens and memory, basically turn them into tiny, portable, totally standalone measurement tools.
And the potential applications? We're just scratching the surface. Think about smart agriculture, where you can swap sensors in and out of a field as needed, or elder care, with standardized health monitors that can be easily integrated into a person's home. The possibilities, from green buildings to intelligent transportation, are just immense.
And all of this leaves us with one last big idea to chew on. A standard like IEEE 1451, it's more than just a technical document. It's a foundational building block for the Internet of Things. So the real question is, when every single object, from a bridge to a car to a heart monitor, can sense its environment and speak a common language, what kind of world are we going to build?